putting it simplistically, there aren't limits. And the reason there aren't limits is that our argument is anchored in the physical fact that the scale of the planet, the scale of physical resources, the scale of energy is fundamentally and functionally unlimited for human beings to tap into.
A warm welcome back to Decouple. Today I'm joined by returning guest, Mark Mills. I'm not sure if this is your hat trick or if we're on 4 episodes together now. We'd originally been planning on doing a show revisiting an earlier episode we did on batteries. We're going to talk about EVs, but I happened to be thumbing around for a book to take on a trip with me, and I had bought a copy of The Bottomless Well. The full title, The Twilight of Fuel, The Virtue of Waste, and Why We Will Never Run Out of Energy.
Yeah.
And I packed it in my suitcase. And since then, I've actually read it a couple of times. And when I say since then, really, it's just kind of the last month or so, because it's dense. It's a thick book, provocative title, but delves into all sorts of things: thermodynamics, conservation, efficiency, broader themes of limits and abundance, electric grids, manufacturing. It hints at a lot of your interests and some things that we've touched on. And so I do want to have you back to talk more specifically about EVs and batteries and developments in those fields. But
by the time I get back to talking about those, it'll be irrelevant because the whole trope will have fully self-imploded, but that's okay. We'll do that later.
All right. So in any case, I thought let's revisit this book. And I mean, the book was written or published at least in 2006. So we've got almost 2 decades in that interim. But again, I just found it to be, I think, a real sort of critical contribution to the energy debate, and certainly one that I'm sort of featuring in my compendium of books that enable me to be somewhat energy literate. So if you're okay with that, I'd love to dive into this book a little bit. And maybe we could start just by, again, time traveling to 2006. You're writing a book called The Bottomless Well in the context of oil prices going through the roof. This is pre-shale revolution. And I think, in response to a lot of ideas coming out of the 1970s OPEC crisis. So maybe you can sort of situate yourself when you're writing this book and kind of what you're writing it in response to.
Well, first, it's nice that you read it. I appreciate that. And it's interesting. It does continue to sell, not in huge volumes. Like it was technically a bestseller, but technically, I mean, in nonfiction, bestsellers have a much lower bar than in fiction. But it went into bestseller category in science. It's basically a science book, as you know, written for the non-scientist about the engineering and physics of energy. And it's pretty broad ranging. My co-author, Peter Huber, who's since sadly deceased, not because of the evil COVIDs, but he had a degenerative brain disease. Very sad. Peter and I are both co-Canadians. I'm originally Canadian. He was originally Canadian. He's a U.S. citizen. He went to MIT and taught thermodynamics while he got his law degree at Harvard simultaneously. So Peter was a certifiably smart guy. He was, I think, I've met Nobel laureates. I've worked with them when I was in the White House Science Office. I've said this, and I wrote this in my eulogy to him a couple of years ago when he died in City Journal. For those who didn't see it, I'd like to point people to it because he was an unusual human, a great loss to us. But he was a true polymath, brilliant jurist, a brilliant trained thermodynamicist. He knew BS when he smelled it and saw it, both in the legal front and the technology front. And we wrote a technology investment newsletter together to give you what this is relevant to the book for a number of years, called the Digital Power Report, all issues of which are at my Tech Pundit website. So you can see what we thought about predicting the future in real time to see whether we were right or wrong, not only in the book, but also in our newsletters where we were making stock recommendations. It was a stock pickers newsletter looking at what was going on in what we call digital power domains, the intersection of technology and energy and power, which has become a hot topic again. At the time we wrote the book, that was the peak year and peak 2 years of the peak oil theory. So at that time, M. King Hubbard's theory that the world would reach peak oil was the headlines all over the place in popular press and in technical press. and we were also then, as you may remember, in the turn of of the 21st century, on the tail end of the same 2 decades of obsession over finding replacements for oil, because the world believed, beginning in 1974 and 79, that we were running out of oil. And so running into the year 2000, hundreds of billions of dollars of U.S. money and Canadian money and European money, collectively trillions spent in the pursuit of avoiding increase the use of oil because we're running out of oil, looking for alternatives, the biofuels, fuel cells, hydrogen, all very similar territory to where we are today. But the difference today is we're worried about using too much oil, but then we were worried about running out of oil.
Right.
But regardless of the motivation, the pursuits were all driven on the same goal. How do we transition to a world where we don't have enough oil, or we shouldn't use it? So that's what motivated us, because there was a lot of very silly things being said about energy at the fundamental level of the physics and engineering of energy machines. And so when he and I thought about how we'd write this book together, and it's the only book I've co-authored. He co-authored one later, but co-authoring's hard. Often co-authors are titular, right? There's 2 or 3 names, but somebody wrote the book and the other is attaching it to it for, they give advice and they're there for PR purposes and whatever. In Peter's and my case, we wrote our investment newsletter and we wrote the book as true co-authors. It was a lot of work, a lot more work. I'd write something, I'd email it to him, he'd overwrite it, he'd send it back to me, I'd overwrite it, and we just do the iterations till we converged on what we agreed on, both technically and in terms of style and substance. And it results in something that, if you read Peter's work, it reads a little different than the book. And if you read what I've written since, it reads the tone and flavor, the style is a little different because it is co-authored. So we wanted to write a book that was, and we thought, do we write what you would call today a Fox News or a CNN book? You write a book that you want people to buy lots of because it's a hot topic that people are talking about today, but it'll get lots of people buy it and it'll just disappear in 6 months. We'll forget the title of the book ever existed. We didn't want to write a book like that, even though you can make more money writing a book like that. We wanted to write a book that would stand the test of time, that would be essentially fundamentally educational and speak to the truths of the facts from which you derive your opinions and policies. And I think we succeeded in that. It was assigned by a number of professors, including one at Princeton, as a textbook in some classes, as the other side, because at that time, the prevailing wisdom was that we were running out of oil and all this stuff. And we correctly predicted the shale revolution in its framing, not in the specifics. We didn't have a chapter in the shale revolution. What we pointed out was that, as I've said many times since, is that there's an infinite supply of energy for all practical purposes in the universe we live in, and including on Earth. Energy is all around us. Energy is the very fabric of the universe we live in. Matter is an intermediate form of energy. You can destroy matter, but you can't destroy energy. The first law of thermodynamics, right, is one that Einstein said will stand the test of time, not the laws of relativity. So matter is, and energy are everywhere and everything, but the energy sources we have all come from information, our understanding of the nature of nature, and our ability to build machines to tap into what nature has for free. It's the machines that cost the money. It's the machines that require our intellect to know to build in the first place. You wouldn't know to make a fission machine till you knew fission was possible. You wouldn't know how to make a combustion machine till you knew that internal combustion was different than external combustion, that kind of thing. Mm-hmm. And then you have to know things about materials, material science, and mechanics, and control systems, and thermodynamics. But all of it's about improving and designing machinery that you locate somewhere where there are natural energy flows and where then consume with the two sides of energy. How to provide it when and where we need it in a way we can afford it. And then how to use it. So energy machines are always in the two buckets. Excuse me, energy producing machines, energy using machines. And both of them involve the physics of energy and are bound by the laws of thermodynamics. And so we wrote the book because whether it's about illumination or manufacturing or cars or flying, you need to know about those two aspects of energy, but they're all dominated by the fundamental physics and thermodynamics of the universe we live in. And they dictate the limits to what you can do. And so we didn't write a limits title. There's no limits to title, right? But what we talked about were the shibboleths, the received wisdoms that were just silly, as well as things that people didn't think about, as you know. By the way, if we approached, before Peter died, we approached the publisher about doing a second edition where the goal would be not to rewrite the book, but to update the charts, because the charts by definition really only cover data to the year 2000 or so. And then to add an addendum to each chapter, leave the chapters alone except for updating charts. Mm-hmm. And each addendum would essentially answer the question implicitly, what's different? I mean, not to think of, what did we get wrong? What did we get right? And he and I talked about this. We don't think we got anything wrong. I mean, it's just physics hasn't changed since then. But there are some things that have changed since then. Some machines have gotten better or not better in the way we thought. And there's been some new vectors that are subtle, but not profound. But it would be interesting to do that. They turned us down. They control the way the contracts are written in the pre-digital book days, because this contract was written in 2002 or so, is that they have publishing rights as long as the book is being sold. So because you bought the damn thing, it's still being sold, and therefore, right. So I might, I may take another bite at the apple and see if I can convince them to let me, even though Peter's now demised. He and I mapped out what we would do. We wrote the new introduction for the second edition. Right. Maybe it'd be nice to do, because we're back in the same debates for the same reasons. I mean, it's different animating reasons, as you know, but the same. What do we do? Can we get off oil? Can we make things more efficient? And does efficiency solve the problem? All the usual things. The relationship of energy to economic growth. All these things are exactly the same.
Mm-hmm, mm-hmm. Yeah, I mean, the persistence of the arguments is quite impressive. The ability to forget, rebound effect, and Jevons paradox. It's such a truism, but it's kind of a many-headed hydra that comes up again and again, and that you kind of have to slay. But yeah, I'm really kind of interested, because I wasn't around in the 70s and interacting with folks. I mean, Amory Lovins is still around, and
he is
less prolific than he was a decade ago.
And he's just as wrong now as he was then.
Right. But yeah, I mean, maybe just by way of framing again, you kind of outline these two archetypes of the lethargists and the cornucopians. So maybe just take a moment to kind of lay the landscape there. I do find archetypes are useful. They kind of depersonalize the debate and just make this much more about the ideas rather than the personality. So just take a second to kind of introduce that concept.
Yeah, I mean, that's why we did that. I mean, it's not about people. Amory Lovins is as we would view as one of the lethargists, but in the language of my new book, as you know, I call them the new normalists, and I changed the word from lethargists to new normalists. But the point is the same, right? At that time, we were not that far off the publication of the Club of Rome's Limits to Growth, and then shortly, that was a 73 book. And then followed, I think it's 79 or 80, with The End of the Age of Waste, which was their sequel. And essentially framing the modern thinking about the limits to growth, because of the limits of the planetary ability, not only to sustain the growth of billions of people, but actually physically have the resources. So there were two parallel, there were two sides of the exact same coin for the lethargists, that they didn't see it was possible for the planet to supply the quantities of things needed to humans, the limits, and that the environment didn't have the capacity to absorb the insults humans impose on nature. Again, limits. So they were degrowthers and anti-growthers, which are coming back into vogue. I mean, the degrowthers and anti-growthers are back out of the woodwork, saying the same things again about how we can have growth, economic growth of some kind, without having physical energy growth or GDP growth, right? And some of them are more overt than that. But that's the lethargy. The lethargists were the Malthusians, that we have limits. The Cornucopians, amongst which we counted ourselves, and the first one to be leveled with the invective, although it was seen as an invective then, was Julian Simon, who I knew was a friend and actually a neighbor, lived across the street from me, who was an economist who published prolifically initially about immigration issues, interestingly. That's where he began his career. Then he got involved in resource and energy issues and had that famous bet with Paul Ehrlich.
Yeah.
So Julian was seen as Peter and I were, and am now, a cornucopian, and is that there are no, and again, putting it simplistically, there aren't limits. And the reason there aren't limits is that our argument is anchored in the physical fact that the scale of the planet, the scale of physical resources, the scale of energy is fundamentally and functionally unlimited for human beings to tap into. Those who, throw out numbers that we're using, and we're using billions of tons of materials and millions of acres of land, all true. But when you put that as a percentage of the amount of available resource on the planet, the amount of energy that we use, is the rounding error, trivial, in the noise. Our ability to tap into that is what we know. It's what we could know potentially is essentially infinite. To pretend we've discovered everything about nature, that we know everything. I mean, you as a doctor know how little we really know about how you know a lot more than people a century ago about how the body operates, but you know full well we have a lot to learn, and the more we learn, the more information we have, the better we get at solving problems and dealing with nature's insults. So the cornucopians live in the world that there's unlimited ability to do that. It's human pursuit of knowledge, and that the result of that has always been, the data show this, is a reduction in our net footprint, that we get better at insulting nature, more efficient at using its resources, and knowing where bad things can happen. And, we get wealthier, and the wealth allows us to do that as well in absolute terms. And then it also allows us to do in relative terms. So the cornucopians are energy abundance and material abundance fueling human well-being. And the lethargists believe that can't happen at the scales that we think it can. And that the only solution, and I'm simplifying, but it's pretty close to accurate, is to constrain growth and manage growth and tell people what they can do and can't do and direct society. So that also bifurcates around political, philosophical ideas too. The leftists tend to be statists and control freaks, and the cornucopians tend to be more free market, even bending into libertarians, but more free market, trusting into the good nature and imagination of human beings, recognizing that people do dopey things and evil things, and we require, the cornucopians don't think we require regulations, environmental rules. We just have a disagreement about the extent of, there's a distinction with a difference about, call it guardrails versus prescriptive.
Right.
And again, you could use medical analogies. You have a patient that you don't know exactly what they should do, but generally the guardrails, they shouldn't be obese, should exercise. There's the guardrail reality versus the hyperspecificity of a particular disease. This is true in societies. We have the guardrails of how you get more energy efficiently, economically. And episodically, you have a very specific problem that you have to solve. That's always true, and we're good at doing that, but it's a philosophical difference. So that we probably detected that the underlying theme in the book, that we were pushing the cornucopian and the centrality of how knowledge and information about these systems continues to advance our capacities.
So, baked into the title, the Twilight of Fuel, is this idea that we use the majority of our energy to purify energy, to make it into more and more useful forms of energy, to drive technological processes that are more and more sensitive, lasers, microprocessors, et cetera. Yeah. And it's this kind of application of logic, as you're mentioning. You go right to James Watt's steam engine and I'm blanking on the name, the governor.
Yes, right.
That allows that. Let's chat a bit about that, because, there's these energy or pyramids of waste that you document in charts, looking at, these base levels in terms of coal and going right up into really refined forms of energy, like the electricity on a microprocessor. It's very reminiscent of ecological kind of trophic pyramids, and you actually have that graph as well. This isn't just my observation.
Right.
You still need a tremendous amount of that base fuel in order to distill upwards.
Yeah.
So I think the book is arguing that the price of the the primary fuel is not as important, obviously, as everything you're adding in, but it still has an importance. And I think, we've seen a change from peak oil theorists to peak cheap oil theorists. And I'm just wondering if you can sort of explore some of those ideas. I know this is a bit of a smorgasbord of a question, but I feel like you do well with those.
And you're right. You sussed out, you sniffed out the distinction with the difference, right? The peak oil people are still out there, but they're mostly saying it's peak affordable oil. Mm-hmm. And that's an important distinction because price is what matters ultimately. I'm tempted to write a book called The Physics of Money, and I've given lectures called The Physics of Money because in the end, the metric that matters is money. What does it cost us to sustain life and do things that we like, that are entertaining, valuable? All the things that happen in life have a cost, and the cost is a measure of human time, fundamentally, and innovation. Because we get more with more innovation. I'm not, being a Pollyanna. There aren't all the yin and yang, the plowshare and sword problems are always with us, but that's the arc of history. So quickly, in terms of before I get to the evolution of the debate to peak cheap oil versus peak oil, the twilight of fuel points to the reality and the goal that the cost and effort, especially the cost of energy, should disappear into the twilight of our everyday life. That for most of human history, up until the last half a century to century and a half, roughly 150 years, somewhere between 70 and 90% of all of the world's economies, the share of the economic output of all the world's economies was devoted to buying and acquiring food and fuel. Food is human fuel, and non-food fuel is needed to make human fuel and to do things. Mm-hmm. So the share of GDP historically, we talk about this in the book, and I've written about it since, utterly consumed, no pun intended, by food and fuel, until the Industrial Revolution, which is really the hydrocarbon revolution. They're the same thing. There was an Industrial Revolution in the Middle Ages around mechanical power, the development of camshafts, gearing for windmills and water mills. And it was a consequential revolution economically. It propelled the Middle Ages into extraordinary advances in wealth. But it could only go so far because it was mechanically based on moving wind and moving water and external combustion, pre-steam engine, pre-combustion engine. So the twilight of fuel is pointing out a factual point and a goal. That's what we want, because acquiring energy, food and fuel, into the twilight means that the money is left available now. It can be used for other purposes: education, healthcare, entertainment, conveniences, protecting the environment. All the wealth that's generated now can be directed at things other than acquiring food and fuel. So increasing the cost of energy is, in our view, a priori, immoral, and a reversion to prehistoric, pre-modern times, which is very bad. So money matters. So that's why the twilight number was really a moral and an economic statement of fact and goal. Now, the subtitle, The Virtue of Waste, gets to your pyramids, that we were pointing to the obsession then, which is returned, with pursuit of energy efficiency, with the constant claim that our energy systems are inefficient. Look at how much of the primary energy we have and how much of it ends up as useful work. Useful work is a mile of driving, a pound of steel, an hour of Zoom time, an hour of supercompute time. The energy at the beginning was 1,000 units. What doesn't matter what the units are. And the actual energy you use at the end is, say, 10 units. And that means that all those in-betweens are wasted, and therefore we should look to save those. We should fix that problem, quote unquote. Mm-hmm. We pointed out that's not a problem. That's a measure of progress, because we use the word you reuse as they use energy to refine energy. That is, the efficiency of going from A to B, heat to motion. You actually consume energy to get the goal, which is the energetics of kinetic energy. That's because in the physics of the universe we live in, all conversions involve an energy loss, or put differently, you put energy to work, we're calling that a loss. This is a nomenclature problem. So it's not a loss. It is a loss from the original starting point. It's an energy cost to convert one energy form to another. So, and we use the lasers as an archetypal example, but lighting is the same. But get to take the photons, which are thermal photons, infrared photons that heat produces. These don't do much good for eye surgery with a laser. It's self-evident as you stated. So how do I get those thermal photons, which is heat from a laser, to become highly organized, right, stripped of entropy laser photons? They're both photons, and they're both forms of energy. How do I get those? Well, I end up with an idea that was incredible, which is highly organized photons are called lasers, which have unique properties. They can cut steel, communicate, send signals, measure things, create all kinds of bizarre magical things emerge from laser photons. But the machinery required to make laser photons has to refine the primary energy at an energy cost into the final form of a laser photon. And that's the pyramid. The first order is you have to make the heat to make the electricity, because lasers are powered electrically. So you have energy is consumed to make electricity. So that's inefficient. No, it's not. It's inefficient if you use a conversion process that consumes half the energy versus uses only 20% of it. You can improve the efficiency of that process up to the physics limit of the process itself, which are well known, by the way, for each step in a process. So I go from heat to motion, from motion to electricity, from electricity to lasers. Each of those things involves a machine that we've invented and uses energy to cause that conversion. And at the end, you've got this, quote, waste. Now, where the waste is, as I said, is in your inability to do it the most efficient way possible in the laws of physics, because we just can't make a machine to do that. But it's not waste in that sense. And then to get the part that's waste out of the system, to pursue the most efficient part, always involves different kinds of machineries, which have a cost, an economic cost. So then you're into the whole domain, which we wrote about in the book and written about many times since, is, okay, what price? You could have today, you can buy a far more efficient internal combustion engine than the average car exists. We've already built them. So the average automobile conversion of thermal energy and gasoline into mechanical energy spinning a drive shaft, that's the essential process. The average efficiency is about 25%. So that machinery is spending 75% of the thermal energy in the gasoline to make that 25%. Okay, but I can make a machine that costs twice as much that is twice as good. It does 50%. It's just an economic decision. Do you want to buy a car with an engine that costs twice as much? Well, most people don't. So those kind of cars don't get purchased. You can impose the requirement on people that do that because you don't like them burning gasoline. That's a political decision and a whole set of other. But it doesn't change the fact that the actual thermodynamic efficiency of the best engines are dictated by laws of physics. And every machine you build that sort of chases the boundaries of physics typically costs more, has an economic cost, which means you're taking money out of the system that could have been used for, say, healthcare, because money is a limited commodity, because money is a reflection of human time. So we try to explain, you're balancing these two things. You're chasing the laws of physics, which have limits, and you're chasing social and economic metrics, which are derivative from what you're allowed to do. But it doesn't change the notion we're trying to push is you're not wasting energy. You're choosing to consume energy to produce a different form of energy which has more economic value, more technical value, more social value. The conversion of heat into motion is a lot more useful than conversion to drive a vehicle. I mean, you could ride a horse. The reason the car was better than the horse, and you can measure the energetics of a horse too, because it's a biological machine. It consumes fuel and energy, and muscles work at certain efficiencies. And in fact, in the grant, we put this calculation in our book. If you calculate the total amount of land used per person mile of travel, the horse is a means of transportation and pure energy and land use is far worse than a car. That it uses more land per person mile. Well, that shouldn't be particularly surprising, because the reason that very few people had horses and buggies is because they consumed a lot of resources per unit miles. Only small use was feasible, and they were expensive. And we made transportation cheaper. Therefore, more people traveled. And there are those, the lethargists, who don't like that. They think it's really bad that we're doing that. We're not in that camp. But even when you get to that, that was that we were trying to illuminate these two odd language choices that we have. So you said the Jevons effect, the Jevons paradox, which if you check in your Dr. Google machine, I think you'll find the occurrence of Jevons paradox in the literature was non-existent prior to the publication of our book, until far further back in time when Jevons wrote his seminal essay in the 19th century. It got a lot of attention, relatively speaking. Nobody paying attention to it for a century. And we exhumed his literature in our book, and it became very commonly written about after that, because Jevons had written about the efficiency phenomena, which has to do with the consumption of energy to refine energy, in the sense that at that time, everyone was worried that England was going to run out of coal. It was the coal age, because we were using so much coal to do so much of the productive value of steam engines. So he observed that improving the efficiency of the engine, the steam engine, would lead to more coal consumption. And he wrote in his paper, we went back, you can still find the original paper online as a PDF. He wrote, that may seem like a paradox. He wasn't stupid, but it's not, because the improvement in efficiency is improved the economic value of that machine, made its output cheaper, and therefore more of it will be used. Hence the economist language, rebound. But this is another example of economists don't get physics or human nature. It's not a rebound. This is silly. It's only a rebound if you're in a mental narrow box that your goal in the efficiency improvement was to cut energy use. Therefore, when you do the efficiency improvement, you find energy use goes up because society uses more of the thing because it's cheaper. That has it backwards. Society wouldn't have gotten more use out of the thing if it were not for the fact of the efficiency improvement. The goal of the efficiency improvement is to increase the utilization of the thing. That's why engineers do that, except in our now intellectually constipated world where we only think in terms of cutting energy use, which is then brings us back to why we called the book The Bottomless Well, because the goal is never to cut energy use. The goal is to improve the efficacy of providing human flourishing and greater use of machines that are productive and valuable for human beings, which always leads to more energy use, not less, precisely because of the virtue of waste. That is, the virtue of becoming more efficient on using energy to do conversions. That is what we've misnamed waste.
Mm-hmm. So efficiency is good because it allows us to do more, not because it allows us to save energy, essentially. Right. One thing I wanted to run past you, there's a prolific guy on LinkedIn named Paul Martin who talks a lot about those committing the sort of second sin of thermodynamics. And he's talking a lot about Václav Smil here, who frequently writes about the near impossibility or a lot of skepticism about achieving net zero on any kind of decadal or even century timeline, and talks a lot about, primary energy, 84% of primary energy is still fossil fuels. Well, Paul Martin will say, you're talking energy, not exergy. And that's kind of, I guess, what you're referring to in terms of that useful work that is at the top of that pyramid. And the task of decarbonization, according to thinkers like this gentleman, Paul Martin, is actually half to 2/3 easier, because if you're not using heat engines through fossil fuel combustion, but using things like wind and solar, there's far less loss there in terms of efficiencies. Can you respond to that? I mean, there's obviously a lot of processes, industrial processes that we just need heat for, and it's pretty cheap to combust fossil fuels to get those. But I'd love to kind of hear your response to that thesis. I'm guessing you've heard it before. But. Yeah,
well, Václav Smil, I've known him for a long time, another Canadian, brilliant, fantastically insightful analyst and writer. And he has written, as you said, and in fact, very directly, that the idea of an energy transition as framed is not possible. I've written papers called Magical Thinking because of that. He has too. he and I are on the different. He's more of a lethargist, by the way. He's a
Yeah,
realistic
yeah,
lethargist. I'm a
yeah.
realistic optimist, and
There's camps here.
but we both occupy the same camp of realism, which is no matter whether you think it's good or bad that we're using more energy, we're not going to change the fundamental energetics of society away from hydrocarbons. It's not possible. Now, and the reason it's not possible is that people like Martin are making a category error. Not only are there many processes for which we do not have combustion alternatives at all, or the combustion alternatives are profoundly more expensive. The other category, and that's just a fact, that's where we are. So hydrogen would be a good example, the obsession over hydrogen. It's roughly 400 to 500%, realistically more like 1,000% more expensive than natural gas. And to get it to parity without subsidies, which is not a way to get it to parity, to get it to real fundamental physics, engineering economic parity, requires breakthroughs in catalysts and electrolysis for which we have no visible solution. Doesn't mean it can't ever happen, but there's no evidence that we know how to do that. The rate of improvement in that domain is trivial compared to what's required. It's that kind of thing Vasov writes about. Also, there's many processes like in steel making that and fertilizer production that are simply either impossible or stunningly expensive, like 10,000% more expensive than when using with hydrocarbons. So let's call that roughly half of the energy world. The other half of the energy world, you could electrify, which is where the thesis comes in. And again, you just follow the money, and not just how much more expensive is it, but does it change the operational modality of the things you're doing in a way that has social economic consequence, which it typically does. So you can rationalize that we should do it anyway, but that you can't. That's okay. That's a political, social argument as opposed to a factual argument. But the trope that combustion is inherently less efficient than wind and solar is a silly trope. It's failure to draw the right boundaries around both where you're starting and where you end up.
Yeah.
I think that the fundamental challenge are the boundary conditions, right? You have to where are we starting with to measure inefficiencies? So you have to look at the whole system. So if you're looking at the energy inherent in hydrocarbon molecules, which is really quite remarkable, and as a starting point, it's 50-fold higher than the fundamental energy available in the molecules of a lithiated chemistry for batteries, which is why you're not going to see Boeing 777s powered by lithium batteries, because you need high energy density to fly airplanes. Small airplanes, short distances, sure, but not big stuff. And that's why cars have a disadvantage, right? It's a half-ton fuel tank instead of a 60-pound fuel tank. That tells you all you need to know about energy density of lithiated chemicals versus hydrocarbons. But you say, well, yeah, but then the electric motor is 90% efficient. Internal combustion engine is 25% efficient. Well, first we have to take the best internal combustion engine, which is 50% efficient. So then I'm taking a half-ton thing with a 90% conversion versus an 80-pound thing with a 50% conversion. Which is better? I mean, duh, this is arithmetic. The internal combustion engine beats the pants off in terms of total system efficiency and weight, which matters because it's materials and it's energy. But to go back to the solar wind thing, let's use solar because it's the most popular thing. So the starting point are the solar photons arriving at Earth. And the starting point is that's the inherent energy available. And the starting point for the combustion engines are the molecules, the molecular energy density of the molecules. So yeah, we take the molecular energy density molecules, and the very best engines, by the way, we can convert 70% of them into useful motion. That's the thermodynamics limit is in the 80% range, roughly.
That's the Carnot limit. Is that
the Carnot
correct?
Limit? So to get the more conversion efficiency with combustion, you raise temperature. That's what Carnot tells you. And as you raise temperature, you need different materials to stand the higher temperature. Yeah. But if you're making an engine for space travel, you really want high conversion efficiencies, and the conversion efficiencies are very, very high. But let's just do the best car. Is 50% of the thermal energy that's inherent in the combustion is converted into mechanical motion. So 50%, quote, loss. All right, that's your cost of getting the thermal energy something useful. Now, what percentage of the available energy in the photons is converted into useful work, right? The photovoltaic cell. Well, the very best commercial photovoltaic cells are running in the 20, 22%, 25% range. But let's be fair and compare it to the best technical available, cost be damned, right? We can get into high 30s. So, but let's do the best possible in the physics. Starting energy in solar, I got 100 units, and I can convert 30. I get 36 electron units out of it, 36 useful work energy units. With the combustion one, I have 100 units, and I can get 50. So it's better. It's better. It's not maybe better. It is a lot better. If that's all you're obsessed about is inefficiency. So how much better can I make the photovoltaic system? Well, we know it's called the Shockley limit. We know the Shockley quasar. We know the limits. We know how far you can't make photovoltaic cells 50% efficient, much more than 50% efficient, but you can get beyond there with some very highly specialized multi-junction cells. The same is true in combustion engines, right? We can make them push towards the Carnot limits in 80%. But the limits for combustion are actually higher than the limits for photovoltaic. And the concentration of the energy density of the inherent materials is much better on the combustion side because you have a diffuse source. When you then measure, now if the boundary conditions properly, how much energy, this is the sort of the energy debt issue, which matters. How much energy do I have to expend to make the material to collect the energy and do the conversion? Okay, with internal combustion engine, it's iron and steel largely, a little bit of nickel. And so it has you have an energy cost in acquiring and refining the materials to make the conversion in the first place. With internal combustion stuff, it's a very low energy cost. As the front end costs are 10% to 5 to 10% of the total system costs, energy costs. In the wind and solar, it flips. There's an enormous energy cost to photovoltaics, not just because the photovoltaic silicon itself is made by combusting coal in China, by the way, where electricity is cheap. Is it making polysilicon for pure grade silicon is about triple the energy intensity of making steel. And I have to make more of it than I made of the steel because the energy density of the arriving material is low. The photonic energy density of the surface of the Earth is low because that's how life survives. The energy density of hydrocarbons is high because it doesn't. It's just the nature of the liquid chemicals, the liquids. So when you count that, you have a further debt. So when you're doing and I'm not counting money ends up mattering the most, but in terms of physical material and physical energy inputs, the energetics, when you measure primary photons to moving the vehicle, primary hydrocarbons to moving the vehicle, the internal combustion engine wins on that, amazingly. What they do is make the mistake of counting it only from the electricity, which is like counting only the electricity output from a coal plant and skipping the coal combustion. You have to count the conversion efficiency. It's part of the game. It's part of the physics. So these arguments, again, are predicated on the assumption that conversions efficiencies tell you something meaningful about costs. They're one factor. What's much more meaningful is how do I supply the energy when and where I need it? So in systems at society's level, when the sun's shining, then this is where the real world economics come in. This is why we see everywhere in the world, every state, every province, every country, the rising penetration of wind and solar is associated with higher grid costs. It's not a temporary glitch. It's a nature of the phenomena of episodic energy. So converting episodic energy into reliable energy is what civilization's been all about. Having food grow when you don't need it is irrelevant. You have to store it for when you need it, but hence refrigeration, preservatives, and all those magical things that gave us food abundance, not production. I'm talking about once you produced it, that's one cost. The other is having it when I need it. So the hand waving that's going on now is to say, well, we just use batteries. Fine. Put aside the cost of batteries for a minute. That has an energy cost. We have to produce the chemicals, the materials, mine it. So that whole energy debt has to go into the solar system that's not in the hydrocarbon system. The equivalent of the hydrocarbon system, by the way, are the steel tanks used to, say, store oil or natural gas. Those have an energy cost. They have an economic cost. Trivial. And they're roughly 100 times cheaper per unit of energy stored than batteries. If you store a pile of coal or a barrel full of oil. It's not complicated to figure out why that's true. It's just a steel can, put oil in it. You stored it. What you have to then, and that allows you to run the engine whenever you want to run it when you need it. The equivalent of that in the solar world is the battery, or, which is what's going on, counting on the other guy to be there anyway, which is the hydrocarbon machines. That's not a transition. That's an economic arbitrage, which may or may not be economically viable, but that's just an economic arbitrage. What we know as a fact today is that economic arbitrage raises the cost of electricity because you've now had to build two parallel systems. This is what Germany did, and any state that's doing this, or province is doing this. You have an existing hydrocarbon system you leave largely untouched. You might shrink it a bit. And you double the size of that system with more wind and solar. It's exactly what Germany did the last 20 years. So now, even if the capital costs of the two are identical, you're delivering the same amount of energy with twice the capital. That's obviously not economically efficient. It's not energy efficient. So if you count spontaneous efficiency, the electric motor with the electrons from the battery is really efficient. Yes, it is. But it's only one piece in the entire system chain to provide reliable transportation on a day-to-day basis for all of society. Are there hyper-specialized situations where the electric-only option is better than the combustion-only option? Yes. And the inverse is also true.
It's so interesting what you're describing there with the example of Germany, and that's maybe one of the more extreme examples, but occurring around the world with the construction of these two parallel systems. And I think one of the arguments,
UK is another one.
UK, California, Australia,
Ontario to some extent is backed off a bit, but yeah.
Yeah. We had our little experiment with those models, directly influenced,
and a political revolution because of it,
and a political backlash. Absolutely. But what you're describing there is, focusing on the fuel side of things. I mean, leave aside the sort of climate benefits or pollution benefits. One of the big economic justifications is that these are fuel sparing technologies. That secondary system exists, but we're using less fuel. There's a focus on conservation of fuel, but in terms of imposing that energetic order, which I think is a big kind of part of what your book focuses on, those costs are massive in terms of turning that intermittent energy, refining it so it can be used in terms of some of our most delicate processes and microprocessors or lasers or whatever, what have you.
Well, they also have an economic cost. So the point of our book, then, the point of what I write about now, is that we need to be honest about what the costs are. If you're proposing a putative benefit for fuel savings, where the goal is to use net less hydrocarbons. By the way, the European experiment, in absolute terms, Europe has spent $1 to $5 trillion on avoiding hydrocarbons in the last 2 decades. Its absolute consumption of hydrocarbons is unchanged. So they haven't decarbonized in that sense, and a great deal of their hydrocarbon use has been exported by deindustrializing, and the industrial activities are done in Indonesia and China and Vietnam. So, but even not counting that, if you look at the total hydrocarbon use of the European continent, it's only slightly lower than it was 20 years ago. So the experiment is not working if that's the putative goal. My principal point is not whether the goal is good or bad. I have an opinion on that. It's a separate issue from. We have to be honest about what it costs, in not just energy and materials, and geopolitical terms. All those things matter in the real world, but in dollar terms. If we have been sold, to be unkind, a bill of goods. In the bill of goods, the trope is that this new stuff, the old stuff, is inherently bad. All its pollution issues and carbon dioxide. The new stuff is inherently better and cheaper. The new stuff is cheaper has been the trope, and it's still repeated over and over again. My point is that's not true. There are net increases in costs. Whether it's going to be true in the future eventually is a whole different thing. Whether it's even possible, which is Václav Smil's and my share the view that it's not. But even if you walk that path and ask how long that takes, you have to be honest about economic costs, because those are the human costs. The ultimate measurement for society is, are we moving society increasingly towards a twilight of fuels where energy is in the background as a cost? Because the money matters. The way we get environmental protection, the way we get resilience, the way we get drug research, and everything in society that requires money And if all of the money is consumed in providing food and fuel, or increasing share of it, you not only decrease the productivity of society, which is wealth destroying, you also decrease the absolute amount of money available for other things. So following the money matters. And claims that it's cheaper and not seeing costs go down means that the claim was false. So you have to now explain yourself. And you can't explain yourself by waving your hand around PowerPoints, claiming exponential change in technologies that cannot change exponentially. Hence why we wrote our book years ago, is that the trope then that there was some kind of magical rapid change in the energetics of systems for producing energy is silly. The only changes that are exponential are in some of the remarkable information-related technologies where you do get exponential changes in the energy efficacy, if you like, of this falls mainly in the domains of information and because of the physics of light, illumination. Those are the two exceptions: information and illumination.
And light. Yeah.
Light is magical. It's the most bizarre feature of the universe that we live in. It's theological, philosophically bizarre. In physics, it's bizarre. Photons are a special case in every respect. Yeah.
Do you have time for one more question, or do you have a hard stop now?
Yeah.
So again, just returning to the question of peak cheap oil.
Well, I didn't answer your peak cheap, did I? No.
Well, yeah. So let's wrap it up on that topic. I mean, conceptually, human beings, just like any organism, will go for the most concentrated, lowest entropy sources of fuel, of nutrients, of resources. And so, we've done that in terms of our oil exploration. We used to just be able to ram a pipe in the ground and get a gusher. And now with offshore oil or fracking, there's obviously a lot of logic and technology applied to it. And remarkably, oil prices have stayed fairly stable despite the increasing intensity of all of that. But in a world, I guess, where again our stocks of high grade mineral ores are declining and the concentration and size of oil deposits that we're discovering are declining, isn't it inevitable that technological process is tugged down by those two other factors in terms of material resource quality and energy and base fuel quality? Or how would you respond to that?
So let's separate, again, a category error. It's a really important one: minerals and energy. We use energy to get minerals. They don't produce energy. They're not. Uranium is the exception. You split the atom, but right. There's always an exception to the rule. It's getting easier, not harder, to find oil. First of all, both onshore and offshore. So the general idea of peak cheap oil is just not true. Technology is accelerating the efficacy of that whole domain. Offshore is a really interesting place where the average time from discovery to production is 10 years for the big offshore platforms. Has dropped to 5 years because of technology. The success rate of finding oil, the old type, deep water, pressurized reservoirs is improved because of technology, supercomputers and imaging. Onshore, the shale revolution is not an exploration project. It's fundamentally a manufacturing project. We're converting what's called a primary resource. The rock is source rock. The oil and gas, the dominant source of oil and gas on the planet, is in the rock itself. And you stimulate it technologically, and you get lots of oil. You don't have to guess where it is. We know where it is, all over the world. So the only question that's true today is the same was true when Peter and I wrote The Bottomless Well, is we know the physical resource is far greater than we can use for shale oil alone. Russia has huge shale fields. China has big shale fields. Argentina has massive shale fields, as big as our Texas Permian Basin. Alberta has big shale fields into the Northwest Territories. These are massive physical resources that exceed our needs by orders of magnitude. Massive. It's just we need better, different technology to get it at prices we would pay. So the question that you're asking now is the same one we asked in our book. To believe that will not become available because we don't think technology will advance and our knowledge about how to build machines and how to extract those resources will never improve, that we're done. We're done with innovation. We're done with discovery. That's the basis of which we're done with finding oil and itself at low and declining real prices as opposed to absolute prices. So I reject that out hand. We did predictably correctly, and then I would make the same claim today. Minerals are a different thing. It's a bigger challenge. I would say I would make the same claim. There's no limit to the amount of minerals the world has that we can access fundamentally. Our ability to find and extract copper at scale at prices we're willing to pay is a much more difficult domain, which is where we should be spending a lot of effort, and will be, because it's an incredibly important mineral resource. And we will go through a period of escalating mineral prices. It's already started. It's going to continue. And we will get through that with some predictable and some unpredictable technological advances, which will collapse the cost of minerals and increase their supply again. Because again, it's not a resource issue; it's a technology issue. So, since all of it's a technology issue, not a fundamental resource issue, you can predict reliably that we'll get it. What you can't predict reliably is whether we'll have the problem solved in 5 years or maybe 50. But in the scope of human history, 50 years would be nothing.
Mark, we could talk all day about this book. Honestly, I've again had to read it 2.5 times at this point. I'm going to finish the second and a half read, I think, in the next few days. Really broad ranging.
Thank you.
You guys end on a bold thesis around the origins of life on the planet, and the Earth as a heat engine, with the interface between the hot face of the planet under the sun and the cold vacuum of space. Lots and lots of interesting food for thought. I really encourage readers to pick up a copy, even though it may prevent you from doing this updated version.
Do it anyway.
Of selling books.
Do it anyway. Thank you.
Yeah. Thanks again for making the time, Mark, and looking forward to our next conversation.
Well, thanks for having me back. We can do it again, and we can talk about. One day we're going to talk about robots in medicine and in warehouses. That'd be fun to do. Thanks for having me on, Chris.
All right. All the best.